So we've been talking about information, how you measure information, and of course you measure information in bits. How you can use information to label things, for instance with barcodes. So you can use information to label things. And then we talked about probability and information. And if I have probabilities for events p sub I, then it says that the amount of information that's associated with its event occurring is minus the sum over I, p sub I, log to the base 2 of p sub I. This beautiful formula that was developed by Maxwell, Boltzmann, and Gibbs back in the middle of the 19th century to talk about the amount of entropy in atoms or molecules. So this is often called S for entropy as well. And then was rediscovered by Claude Shannon in the 1940s to talk about information theory in the abstract and the mathematical theory of communication. In fact, there's a funny story about this that Shannon, when he came up with this formula, minus some p sub I log to the base 2 of p sub I, he went to John von Neumann, the famous mathematician, and he said, "What should I call this quantity?" And von Neumann says, "You should call it h, because that's what Boltzmann called it." But von Neumann, who had a famous memory, apparently forgot that Boltzmann's h, of his famous H theorem, was the same thing but without the minus sign. So it's a negative quantity that gets more and more negative, as opposed to entropy, which is a positive quantity that gets more and more positive. So actually, these fundamental formulas about information theory go back to the mid-19th century, 150 years. But now we'd like to apply them to ideas about communication. And to do that, I'd like to tell you a little bit more about probability. So, we talked about probabilities for events, probably x, x equals it's sunny. Probability of y is it's raining. And we could look at the probability of x, and I'm going to use the notation I introduced for Boolean logic before, is the probability of this thing right here means and, the probability of x and y, or we can also just call this the probability of x, y simultaneously. Keep on streamlining our notation. This is the probability that it's raining, it's sunny, and it's raining. Now, in most places of the world, this is a pretty small probability, but here in Santa Fe, it happens all the time. And as a result, you get rather beautiful rainbows, single, double, triple on a daily basis. So we have, this is what is called the joint probability. The joint probability that it's sunny and it's raining. The joint probability of x and y. And what do we expect of this joint probability? So we have the probability of x and y. And this tells you the probability that it's sunny and it's raining. We can also look at the probability of x and not y. So x and not y. Again, using our notation introduced to us by the famous husband of the daughter of the Surveyor General of the British Raj, George Boole, married to Mary Everest. And we have a relationship which says that the probability of x on its own should be equal to the probability of x and y plus the probability of x and not y. And the probability of x on its own is called the marginal probability. So it's just the probability that it's sunny on its own. So the probability it's sunny on its own is the probability that it's sunny and it's raining, plus the probability that it's sunny and it's not raining. I think this makes some kind of sense. Why is this called the marginal probability? I have no idea, so let's not even worry about it. There's a very nice picture of probabilities in terms of set theory. I don't know about you, but I grew up in the age of new math, where they tried to teach us about set theory and unions of sets and intersections of sets and things like that from starting at a very early age, which means that people of my generation are completely unable to do their tax returns. But for me, dealing a lot with math, it actually has been quite helpful over my career to have learned set theory at the age of 3 or 4, or whatever it was. So we have a picture like this. This is the space, or the set, of all events. Here is the set X, which is the set of events where it's sunny. Here is the set Y, which is the set of events where it's raining. This thing right here is called X intersection Y, which is the set of events where it's both sunny and it's rainy. By contrast, if I look at this right here, this is X union Y, which is a set of events where it's either sunny or rainy. And now you can kind of see where George Boole got his funny cap and cup notation. We compare this with X and Y. X and Y, from a logical standpoint, is essentially the same as this union of these sets. And similarly, X intersection Y is X or Y. So when I take the logical statement corresponding to this set of events, then I write it as X and Y. The set of events is the intersection of it's sunny and it's rainy. X or Y is the intersection of events where it's sunny or it's rainy. And you can have all kinds of, nice pictures. Here's Z, where let's say it's snowy at the same time. It's sunny, it's rainy, and snowy, which I have certainly seen happen here in Santa Fe. This is not so strange. And here we have X intersection Y intersection Z, which is not the empty set in terms of Santa Fe. Okay, so now let's actually look at the kinds of information that are associated with this. Suppose that I have a set of possible events. I'll call one set labeled by I, the other set labeled by J. And now I can look at P of I and J. So this is the case where the first type of event is I and the second type of event is J. And I can define, so you know what, I'm gonna do this slightly different. Let's call these, we'll be slightly fancier. We'll call these events X sub I and events Y sub J. So I labels the different events X, J labels the different events Y. So for instance, X sub I there could be two events, either it's sunny or it's not sunny. So I could be 0 would be it's not sunny, and 1 could be it's sunny. And J could be it's either raining or it's not raining. So there are two possible values of Y. I'm just going to trying to make my life easier. So we have a joint probability distribution, Xi and Yj. This is our joint probability as before. And now we have a joint information, which we'll call I of X and Y. This is the information that's inherent in the joint set of events, X and Y, in our case being sunny or not sunny, raining and not raining. And this just takes the same form as before. We sum over all different possibilities, sunny, not sunny, sunny, raining, not sunny, raining, sunny, not raining, not sunny, not raining. This is why one shouldn't try to enumerate these things. P of xi, yj, logarithm of P of xi, yj. So this is the amount of information that's inherent with these two sets of events together. And of course, we still have this in the, if you like, the marginal information, or the information in X on its own, which is now just the sum over events x on its own of the marginal distribution. Why it's called marginal, I don't know. It's just the probability for x on its own. P of xi log of x2, P of xi. And similarly, we can talk about I of y is minus the sum over j, P of yj log to the base 2 of P of yj. This is the amount of information inherent in whether it's sunny or not sunny. It could be up to a bit of information. If it's probability 1/2 of being sunny or not sunny, then there's a bit of information. Let me tell you, in Santa Fe, there's far less than a bit of information about whether it's sunny or not, because it's sunny here most of the time. Similarly, raining or not raining could be up to a bit of information if each of these probabilities is 1/2. Again, since we're in the high desert here, it's normally not raining, so you have far less than a bit of information in the question of whether it's raining or not raining. So we have joint information constructed out of joint probabilities, marginal informations or informations on the individual variables on their own constructed out of the marginal probabilities. And let me end this little section by defining a very useful quantity which is called the mutual information. The mutual information, which is defined to be Ix, I normally define it with this little colon right in the middle because it looks nice and symmetrical. And we'll see that this isn't symmetrical. It's the information in X plus the information in Y minus the information in X and Y taken together. It's possible to show that this is always greater than or equal to 0. And this mutual information can be thought of the amount of information that the variable x has about y. If x and y are completely uncorrelated, so if it's completely uncorrelated, whether it's sunny or not sunny and raining or not raining, then this will be 0. However, in the case of sunny and not sunny, raining and not raining, they are very correlated in the sense that once you know that it's sunny, it's probably not raining, even though sometimes that does happen here in Santa Fe. And so in that case, you expect to find a large amount of mutual information. In most places, in fact, you'll find that knowing whether it's sunny or not sunny gives you a very good prediction about whether it's raining or it's not raining. Mutual information measures the amount of information that x can tell us about y. It's symmetric, so it tells us the amount of information that y can tell us about x. And another way of thinking about it is that it's the amount of information that x and y hold in common, which is why it's called mutual information.